Full-scale structural and non-structural construction procedure of a multi-story test building at the Englekirk Structural Engineering Shake Center. Module 5, Non-Structural, Egress Systems. Objective 1. To describe the basic types of floor-to-floor access, also termed egress, in a building. Objective 2. To describe stair systems, their details, materials, and installation methods. Objective 3. To describe elevators, their mechanical requirements, safety stopping requirements, and installation methods. In buildings, working stairs and elevators are crucial to facilitate daily travel through the building, and importantly, in times of emergency, they provide the only evacuation route out of the building. As a result, they must be designed to remain operable even under unexpected hazards, such as earthquakes. Using the 5-story cast-in-place reinforced concrete building as an example, this video describes the fabrication and installation process for a common type of stair and elevator system. There are many different types of stairs. The simplest and most commonly used is a staircase with a straight flight, meaning its elevation gain continues along a straight line. However, these stairs are limited in height because the number of treads, the part of the stairway that is stepped on, along a single straight flight is not allowed to exceed 16. An alternative to a straight flight and providing increased efficiency are termed scissor stairs. Scissor stairs turn by 90 and 180 degrees and use wedge-shaped treads rather than rectangular ones on the turn. Other types include arched or curved stairs, both of which resemble the shape of their name. To form the arch shape, the treads in these stairs are wedge-shaped, making them difficult to construct. Perhaps the most complex, however, from a construction perspective, are spiral stairs. When complete, they are quite elegant as they are commonly designed to form a perfect circle. Stairs can be constructed from a number of different materials, however, they are mainly fabricated from concrete, metal, or a hybrid of the two. Metal stairs are most commonly prefabricated of steel sections and assembled on-site, whereas concrete stairs may be constructed in segments at a precast concrete plant and shipped to the site for attachment to the building. Minimum design loads for stairs are consistent with those required of emergency corridors within building structures. In the United States, these are specified as 100 pounds per square foot by the American Society of Civil Engineers Design Code. This minimum load carrying capacity is important to consider during times of emergency such as fire or earthquake, where the egress systems must be able to handle a sudden and large increase in occupant loads. In the 5-story building test, prefabricated metal scissor stairs were used. In this particular scissor arrangement, 2 flights and 1 mid-height landing per floor formed the floor-to-floor stair assembly. These stairs, also referred to as half-landing stairs, reduce the quantity of treads in one flight and make walking more comfortable. Because they are very functional, safe, and most importantly compact in space, scissor stairs are used quite commonly. During installation of the stairs on the first level, the lower flight was connected via a bolted connection to the floor slab at the ground level and to a landing supported vertically by 4 landing posts. The ends of the 4 posts were welded at their bases to the steel embeds, which in turn were connected via bolts to a concrete slab. The landing was erected first, and the lower flight of the stairs was lifted in place by a crane. Similarly, the upper flight was brought in with a crane and bolted to the landing and the second floor. The upper flight was connected to the next floor level by field welding to a steel plate that was cast with the floor slab. This method was repeated for the staircases at subsequent floors. 2 types of elevators that are most commonly used in buildings are hydraulic and traction. Hydraulic elevators consist of the cabin, which is the part of the elevator that carries occupants or other payloads from floor to floor, attached to a hydraulic jack at the bottom of the elevator system. The hydraulic jack is connected to a pump and reservoir, which is below the lowest floor of the building. This kind of elevator system is mostly used in single-family residences. The second and more commonly used elevator system, which was utilized in the 5-story test building, is a traction elevator. Traction systems consist of cables that connect to the top of the cabin on one end and to an electric motor at the top of the elevator shaft on the other end. This electric motor is attached to counterweights, which help lift and lower the cabin to the desired floor. In the 5-story test building, the counterweights were assembled with steel blocks and in total weighed approximately 1,700 kilograms. The steel cables in a traction elevator loop around the sheave, which is a pulley with grooves around its circumference. These grooves grip onto the steel cables so that they move together as one. The sheave is connected to the electric motor. When the electric motor moves up in one direction, the sheave raises the elevator, and when the electric motor moves in the opposite direction, the sheave lowers the elevator. The counterweight plays a big role while the elevator is moving. The counterweight is designed to weigh approximately the same as the cabin when it is filled to 40% capacity, which is the optimum design to conserve energy by having equal loads on each side of the sheave. Both the cabin and counterweight ride on guide rails, which run along the sides of the elevator to prevent the cabin and counterweight from swaying and to serve as a safety system in case of an emergency. Before the elevator can be installed, during the construction of the skeleton of the building, an elevator shaft must be created and provided through the path in which the elevator is intended to travel. In the 5-story test building, the elevator shaft spanned from the ground level through each floor to the roof level. It was enclosed by concrete walls on the east and west sides and by metal stud walls on the north and south sides. In addition to perforating the floor slabs in which the elevator must travel to form this shaft, the ground level must be dropped to form a pit in which the base of the cabin can rest, drainage can be collected, and potentially additional equipment to service the elevator can be stored. When constructing an elevator shaft, there are usually 5 steps involved. The first step is to install the buffer, basework platform, and the hoist system. In this case, the hoist system for the traction elevator consisted of the electric motor. Step 2 involves installing the guide rails and brackets. Guide rails function as vertical internal tracks fixed on opposite ends of the shaft. One guides the elevator cabin, while the other guides the counterweight connected to the electric motor. The third step is to place the counterweight frame, including an initial counterweight. The rest of the counterweight would be applied after the cabin was brought in. In addition, 4 guide shoes are secured at the frame corners to assist the counterweight from any lateral movement and prevent damage to the building, such as in an earthquake. The fourth step involves installing the drive and control systems. Once the drive and control systems are fully functioning, the elevator cabin is brought in and the remaining counterweight load is attached. A total of 70 steel plates, weighing approximately 200 newtons each, were used as counterweight. When it comes to egress systems, safety is a very important issue since they are the primary systems used for emergency evacuation. To assess safety from a designer's perspective, the term factor of safety is used to describe the capacity of a structural system beyond what is expected. The factor of safety is therefore dependent on the strength of the materials and the various connections used in the building, as well as the loads expected in the building. Most design situations associated with the building's components strive for a factor of safety between 2 and 3. In the case of elevators, however, the industrial standard is to design for a factor of safety of at least 11. This means that if an elevator has a maximum capacity of 20 people with a combined weight of 1,500 kilograms, then it can actually hold over 220 people or 16,500 kilograms before it fails. While 220 people will not likely fit in an elevator, this analogy demonstrates how various building components are over-designed to ensure safety. Another safety measure adopted in elevators is a built-in braking system that grabs onto the rail when the cabin is moving at high speeds. In conclusion, this video, which is the 5th in a series utilizing data collected from a full-scale building test program conducted at the University of California, San Diego, was intended to present the following. 1. To describe the basic types of floor-to-floor access in a building. 2. To describe the stair systems, their details, the material they are made out of, and installation methods. And 3. Finally, to describe elevators, their mechanical requirements, safety stopping requirements, and installation methods.